Hi, I'm Guillermo Angeres. I'm here to present Replicating Monotonic Payoffs Without Oracles. This was work done jointly with Alex Evans and Tarun Chitra from Bain Capital Crypto and Gauntlet Networks, respectively. And I guess I was at Stanford at the time, and now I am also at Bain Capital Crypto. So I guess to first things first, kind of set the stage, what does the title even mean? So usually in a centralized finance, right, a bunch of the notions is to replicate traditional financial instruments and sometimes not so traditional financial instruments on chain. A lot of the ways that this is done currently is kind of to take the usual mechanisms that traditional finance uses in order to construct specific outcomes. So and these outcomes are often specified in terms of payoffs, right? So in particular, for some object has a payoff, right, which is just depends. It's a function that depends on the price of the asset and then is paid out to a user at some specified time. The point is, a lot of the ways that we're currently or replicating traditional financial instruments on chain rely on this idea of an oracle. It's a trusted intermediary who reports the price. So the contract, a smart contract, which is something to replicate some financial instrument, can query this trusted intermediary. And this ideally trusted intermediary, or hopefully trusted intermediary, reports a price of some asset. And then based on whatever is reported, the contract does something, right, in order to achieve the desired payoff or to achieve the desired behavior. Of course, one easy, or maybe not so easy, but very important problem that appears with this is that in some cases, a trusted intermediary might have an incentive to lie, right? Or can be easily manipulated, or is not so expensive to manipulate, etc. And in those cases, it's not clear really what to do, right? Kind of the whole assumption of the system itself assumes this intermediary is trusted, but that's actually not always a great assumption. Usually this becomes especially worrisome when the trusted intermediary is securing more funds for a given contract than they're actually, personally, might get slashed for or might be punished for. So one could imagine that, like, if a trusted intermediary network is secured by a few tens of millions of dollars, but a protocol worth many hundreds of millions of dollars uses a trusted intermediary to secure them, then there might be an incentive to lie, because in the worst case, the trusted quote unquote intermediary, the oracle, might just the worst they can do is lose tens of millions of dollars, but by misreporting a price, they could potentially earn many hundreds. So at the end of the day, right, it's kind of, while the idea of decentralized finance is to decentralize finance, we often require the use of oracles, which correctly report the price. And now, kind of the protocol is in the hands of these, this correctly reported price, or this this notion that the price is always being correctly reported back to the contract. So the whole point of this paper is to show that there is an ever-expanding set of payoffs that we can replicate without the use of oracles. This set of payoffs that we can replicate simply by incentivizing agents to correctly report the price. And in fact, anyone can correctly report the price without any kind of exception. And if they misreport the price, it's actually just strictly worse for them at every point in time. So what exactly that means, we'll get to that in a second. But So outline first, we're going to discuss what, a very important but restricted notion of what a payoff is, right? So what is traditionally considered a payoff in finance? And then we're going to show that, in fact, we can construct from that payoff, we can construct a trading function. So if you're familiar with constant function market makers, this idea will be very natural, but the point of a trading function is kind of this invariant that says anyone can rebalance some assets that I have. So they are allowed to take out some amount of the asset and put in some amount of another asset, such that some function always remains constant. That's called the trading function. And we'll show how this can actually lead to us being able to replicate a given payoff. And here the payoff is going to be given by the user, for example, and then it's going to be fixed ahead of time by the protocol. And then from there, we can construct a trading function, which allows anyone to trade with this trading function. And by construction, this trading function essentially incentivizes people to arbitrage external markets against this, kind of internal small trading function market, also known as a constant function market maker. And then based on that, the user will receive some specified payoff. So not the arbitrageur or the trader, but in fact some user who is part of the protocol, because of this behavior, will receive the desired payoff function. And then we'll see how kind of this leads to a very, very natural protocol, which requires no trust assumptions about oracles. Okay, so again, what happens? What do we want? Well, we want to replicate a payoff function. What is a payoff function? It is a function that maps the non-negative reals to the reals. In this case, it'll be the non-negative reals, but in general, it could be any real number. And the point is that the function f maps some non-negative price to a payoff f of p. And we'll denote the payoff in some numeraire. So p is the price of an asset, and we're just going to call it the asset. And f of p will be denoted in the numeraire. You can think of this as potentially a stable coin like USDC, or more generally any numeraire that you would like to have your payoff in. We will only make actually one assumption, and that is that f is monotonic. So in particular, that f prime is non-negative. Note that f, which is kind of weird, usually in economics, right? There's kind of this idea that these functions have to be concave or convex or something like that. Actually, we make no such assumption here. The only assumption that we make is that f is monotonic. In other words, as the price of the asset increases, the payoff must also at least not decrease. So what is a payoff? Well, we're going to assume that the payoff is given by the black box known as finance. In our case, it was the black box known as Alex Evans, who simply says, hey, these are interesting or important things that we should replicate on chain. So what are some examples of such payoffs? Well, here's one. It's a cash or nothing call. So a cash or nothing call is one at which there is some price, P naught, right? If the price of the asset is below P naught, you get nothing. That's the payoff is 0. And if the price of the asset is above or equal to P naught, then you get a payoff of 1. So $1, for example. There's other cases such as covered calls or power payoffs, right? So power payoffs are one in which the payoff is some exponential or some quadratic, cubic, etc. So any exponent of the underlying price of the asset. And there's many others, of course, so we won't cover them all here. But the point is that the specifics don't actually matter. It just matters that we are given a function f that is monotonic and non-negative. Okay, so let's kind of step back and think of a weird strategy which is going to allow us to cover this payoff. So the idea is, look, if we had perfect control of kind of what happens, how would we ourselves be able to kind of replicate this payoff? So one simple kind of weird idea is that we can allow a trader to hold some amount f of p of the numeraire and some amount, which we will not talk about yet, of the asset. So if I want the payoff f of p, I now have the right to the numeraire side of this pool, right? And then the trader simply is only allowed to trade between kind of this numeraire side of the pool and some asset side of the pool. And the idea is what the trader is going to do, and the trader again is this kind of magical entity, is that as the price changes, the trader is going to buy or sell some amount of the asset and put it, for example, if they sell some amount of the asset, they put the proceeds into the numeraire pool, or if they need to buy some amount of the asset, they take, some amount from the numeraire pool, buy the asset and put the asset into this other box, right? And the point is they need to do that in such a way as to maintain the amount of the numeraire to be equal to f of p at every given price. So as the price goes up and down, they trade and buy such that this pool of asset has exactly the amount f of p. So of course, the next natural question is, great, so we know how much we need for the numeraire. How much of the asset should the trader actually keep? So it turns out the amount needed is actually given by this function. It has a very simple interpretation. So we have f prime of q dq is how much of the numeraire changes for a given price change, dq, so from q to q plus dq. And then the point is, look, if the amount of the numeraire pool needs to increase by f prime of q plus dq, f prime of q times dq, then the amount of asset we have to sell is the amount of the numeraire divided by the price of the asset, right? So the point is, kind of as the price goes up, right, we need to sell, just roughly speaking, the delta of how much we expect the numeraire to increase by, divided by the price of the asset. right? If we take this limit and then take the integral, we get g of p. The point is, the trader now has this kind of interesting problem, which is an implicit portfolio at every price. So the trader has some amount f of p, so at every price p, the trader has some amount of the numeraire f of p and some amount of the asset g of p. And one very natural kind of object to look at is this set of possible portfolios, which is, S is the set is the graph of all possible portfolios where, for example, the x-axis is the amount of numeraire and the y-axis is the amount of the asset. And this is simply the set of all of the possible portfolios along this kind of curve. So this will get us to kind of a very natural notion of a trading function. Again, if you're familiar with constant function market makers, this is going to be, you kind of already probably know the punchline. But more generally, the point is we're going to construct an automated market maker, which is defined by this trading function, such that when people trade with this market, so people are always incentivized to arbitrage this market against an external market in order to keep this portfolio kind of in balance. So what I mean by in balance is that it means that the numeraire side of this portfolio always has some amount f of p if there's an external market that is reporting that the asset is priced at p. So this does not require, any trust assumptions, because the point is people will simply be incentivized to make a profit by arbitraging this portfolio or this kind of weird trading thing against the external market. And we'll specify exactly what that means in a second, but that's kind of the high level idea. Okay, so getting back to it, the set of possible portfolios is the set S, which draws a graph of the possible, kind of numeraire assets numeraire versus asset here. And it can be written in a simple way. The point is a point R1, R2 belongs in this set if and only if kind of this function is equal to 0. So what is this function? It's not that difficult to interpret. You can think about it as if you look at the set, right? And we say, okay, what is R2? Well, R2 implies some price P. What is the price? That is G inverse of R2. And then you'd better hope that if you evaluate F on this implied price, that is equal to the amount of the numeraire that is in this portfolio, right? And so that is in some sense kind of an invariant that must hold for any for any kind of portfolio to be valid, to be in S, right? And so this phi, we're going to call it the trading function. It's sometimes known as the invariant or portfolio invariant or something like that. But the point is a portfolio belongs in the kind of the set of possible portfolios if and only if phi evaluated on that desired portfolio is equal to 0. So here's a weird idea. If we can always enforce that, if anyone is able to kind of propose portfolios, if we can always enforce that this function had better be equal to 0, then in some sense, we've kind of restricted, we may be able to kind of allow anyone to rebalance this portfolio, right? So what do I mean? I mean that if you let anyone kind of remove some amount of asset 1 and then put in some amount of asset 2 or vice versa, and they can only do so in such a way that this function evaluates to 0, then in some sense, at every point, we're sure that this is going to be a desired portfolio, right? It might not be the right desired portfolio. So if there's an external market with some price P, maybe they're incentivized to do something weird and rebalance it to kind of the wrong portfolio allocation. But in general, you could imagine that this could potentially lead to some interesting behavior. So the point here is that what we're going to say is any agent can come in, put in some amount of asset 1, take out some amount of asset 2, or vice versa, of this kind of pool of assets, such that this function evaluates to 0 on the new pool of assets, right? So after rebalancing, this function must still evaluate to 0. Certainly prior to rebalancing, it better evaluate to 0 because that was the initial assumption, but after rebalancing, it better equal 0. And so as before, so by the way, if this is kind of general from the literature, but the markets of this form are called constant function market makers. And they're called constant function market makers because one way of thinking about them is that they are simply markets which let you trade asset 1 for asset 2 or vice versa, in such a way that the assets that you trade maintain this kind of fixed function. So Uniswap, Balancer, Curve are all examples of such markets. But kind of leaving that aside, the point is that given this rule, we are always guaranteed that the reserves in these two the reserves of the asset and the numeraire in this pool, or asset 1 and asset 2 and asset 1, are always in the set of possible portfolios. So now the next and final last question is, look, if there's an external market at price P, are we always guaranteed that indeed R1 actually, so that the side of the numeraire actually has the desired payoff at that price? So in other words, is R1 equal to FP? And of course, the spoiler alert is yes, this is true. So in particular, we're going to describe what the arbitrage game is. So the arbitrage game is as before, we let anyone rebalance against some external market, and the price of the external market, the price of the external market quotes, is P. So the point is, there's some greedy agent who attempts to maximize their profit. Turns out it's very easy to see that actually this is equivalent to minimizing the portfolio value at that price. So in other words, the arbitrageur, or this agent, is looking to minimize the sum of the numeraire plus P times the asset. That's the total, numeraire denominated value of the portfolio, subject to the fact that this invariant had better be satisfied, because they are allowed to do rebalance R1 and R2 as much as they want, so long as the invariant is equal to 0. So interestingly, it's very easy to see just by taking the first order optimality conditions that the optimum is actually exactly what we want. It is that in fact R1 will be equal to f of P and R2 will be equal to G of P. The latter doesn't matter as much, but the former is the really important part. And the point is that, by trying to maximize their profit, right, arbitrageurs are actually exactly doing the favor that we need them to do, which is that the numeraire denominated side of the pool actually has some amount f of P whenever the asset of the asset side, or just the asset itself, is worth P in an external market. So the point is, another important thing that's true is that this problem actually has an exact convex formulation. This follows just from the fact that we can relax that equality constraint to an inequality constraint. And you can show that the function phi is actually a convex or a concave function. So in general, it's not difficult to see that, in fact, this problem is not only kind of has the right optimality conditions, but in fact is also extremely easy to solve. So being convex often means that you can solve a problem with very simple heuristics, and these heuristics will actually get you very close to the optimum, if not the optimum. So in other words, again, kind of saying this again, is that arbitrageurs are truly incentivized to rebalance a portfolio correctly. There's no additional incentives needed. So the point is, you don't need any external price oracles or any additional incentives, since people are, just by kind of having their greedy behavior, they're always incentivized to rebalance this pool correctly. Okay, so with that, I guess, ends the major part of the talk. The point is, now we have a framework for which, for any monotonic payoff, F, we have a decentralized, decentralized big quotes, replication method. The point is that this method relies only on external incentives. It doesn't rely on any additional notions of like having anyone try to slash people or trying to, add in money in order to incentivize people to do this, right? It simply is just like, by construction, anyone who wants to, they can just go in and arbitrage these two things, these two pools, and they'll always be incentivized by maximizing their profit to do it correctly. The point is, this leads to a very simple mechanism that's very easy to implement in practice. So there's just, one contract or maybe a few, but they have no external dependence on anything else, except for the fact that they have no external, at least explicit dependence on anything else, right? They only depend on the fact that there needs to exist some other market for this asset somewhere. And that market, whatever its price is, someone will be incentivized to arbitrage it against this portfolio. And the point is that given any reasonable implementation, this has actually very, very strong safety guarantees. Right? So this is a paper we wrote maybe 2 years ago now about what exactly are some of the properties of these constant function market makers. And it turns out you can do kind of pretty much anything to them. They're pretty much bomb-proof in a lot of ways. And at the end of the day, people are always kind of incentivized to just do the right thing, because doing anything else just turns out to be strictly suboptimal. Anyways, thank you so much.